Or there's one other possibility, which is that the pendulum looks like that. But there are only two ways of getting it. In most places, there are only two ways of getting it. In the centre, there are many ways of getting it. We call that degeneracy, and it means that it seems like it's being attracted towards the centre, but it's just a sort of statistical effect, because there are lots of different ways for it to get to the centre. So there are lots of things about the long-term behaviour of this thing that we actually understand very well without having to be able to calculate exactly what it does every time that we set it going. And in fact, that means that if I take now, I can't see, there we are. So earlier on, I actually made a calculation of what I would expect this picture to look like. Now, unfortunately, we've lost half the picture, but I can still compare the other half. If we do that, you can see the kind of patterns that you get out of my prediction, which was based on the maths of all the different forces acting within this pendulum. Actually looks not too bad. I mean, the details aren't the same, but all these kind of general features, like it doesn't go near the top very much, it's attracted towards the centre and so on. And there are more, you know, you can go on forever finding more and more subtle things. Those general patterns are reproduced. Now that's the key thing that means we're actually able to get somewhere with this. All right. The fact is that, okay, we can't predict exactly what's going to happen to the pendulum. And we can't predict exactly what's going to happen to one given blob of dark matter in the universe. But what we can do is understand why, although the predictions in detail break down, the kind of patterns that come out are going to be the same from one version to another. So that applies to the dark matter in the computer as well. Yes, the details go wrong, but the basic patterns that come out are still consistent between our two computers that I showed you earlier on. And in fact, that really is one of the reasons why we do take dark matter, well, that and the fact we don't have any better ideas, but that is one of the reasons we take dark matter seriously, because we can do calculations with it if we just sort of, you know, ignore the fact that we're talking about patterns rather than about specifics. In fact, these galaxy simulations that I'm talking about even go as far as showing us how galaxies form in the real universe. So this is a more complete galaxy simulation which has started from quite early on in the universe and shows how we think galaxies build up. Now we've got everything in here. We've got gas and stars and dust, and we've got dark matter as well, which you can't actually see the way I've drawn it here. I'm trying to draw it as though this is what a telescope would see if it could see the universe evolving. But what we see over time is that you start with lots of little galaxies, and over time they merge together. They're actually being pulled together by their dark matter. They merge together, they form bigger and bigger things, and if you skip forwards through 14 billion years, which is how old we think the universe is, then you end up with a big whirling pool of gas and stars, and you can even fly into it and have a look at what would it be like to live inside this thing. And in fact, it turns out that we're able to build something that looks very much like our own galaxy. This is what a good picture of the night sky looks like. So, despite dark matter being based on some pretty wacky ideas, and despite the fact that actually we can't calculate exactly what happens to dark matter, we can take the ideas that we've come up with and just kind of use them anyway, hope for the best, and we end up with a virtual universe inside a computer that looks very much like our own. So that brings me on to the final example that I wanted to go through of how you can get away, I suppose, with the fact that things are really quite unpredictable. And I promised I would talk about the economy, right? And so I am actually going to talk about the economy. It turns out that physicists were thinking about the economy, and they thought, hey, we can do this, we can do the economy, can't be that hard. So they came up with a model for how the economy works, and the model of the physics model of the economy works like this. So you start out the day, you're in your house, and all your money that you own in the world is all just in piles of cash round you, and then you pick up all of your piles of cash, then you go out the door. And once you get out into the street with your wads of cash, when you see somebody passing you by with their wads of cash, you just throw some at them. You go, oh, way, there you are, there's some money, there's some money, there's some money. You just throw the money around. And also, if somebody throws some money at you, then you take it, obviously. I mean, you're not stupid. So when somebody throws some money at you, you take it. And then at the end of the day, having gone around throwing money around, you go home, you can loosen your tie, you go home, you get home, and you stash your money. That is the physicist's model for the economy. That's it. Now, it sounds a bit stupid, right? A little bit. But it makes some predictions. One prediction you can get out of this model is how rich should people be in general. So if I take all the different families in a country and I find out how much money they have after they've been doing this for a few years, then I can plot it on a graph. If you don't like graphs, it's okay, this bit won't last very long. This is the prediction, okay, that you get from this physicist view of the economy. It's saying that a few people over on the right-hand end make lots and lots and lots of money. It keeps going, you know, off there and probably for about a mile in that direction into the city. And then down at the left-hand end, you have quite a lot of people, in fact, the vast majority of people, making not very much money. And it's just based on that simple idea, that's all it is. So having done that, you then go, okay, let's get some data, because that's what you do with predictions, right? You compare them to data about the real world. So let's get some data about the real world. These guys took the census data from the United States to find out, well, how much money are people actually making? And you can plot that on this graph. Bang. It's absolutely amazingly close. I love the fact that the world's most advanced economy is basically modelled by a bunch of 3-year-olds playing Monopoly. It's mind-blowing. And I think the thing to take away from this is that you can take ideas which are clearly not very sensible, and you can still learn something from them. You can still find out something about the world from ideas that are a bit wacky. Of course you couldn't use this to work out how much money does he earn. Of course you couldn't do that. But you can find out things on average about what goes on average. Very similar to the idea about the dark matter and the idea about the pendulum. Now, finally, I did promise I'd say something about dark energy. This is the last thing I'll bring up. It's a perfect topic, actually, just to bring up in the last 2 minutes. Because dark energy is a whole new thing. It's not the same as dark matter. It's totally separate. And it's based on the following fact. The universe is expanding. That's been known for quite a long time. That just means all the different galaxies that I've shown you in the universe, they're all getting further away from each other over time. But not only is it expanding, it's actually expanding at an accelerating rate. So that means if 2 galaxies are flying apart at a given rate today, then tomorrow they'll be flying apart just a little bit faster. And that is pretty weird, to be honest. I mean, for a start, you can imagine that really requires you to find some energy somewhere. If you want to make things go faster, you need to add some energy in. And so physicists sat down and they thought, right, okay, well, we kind of did okay with the dark matter thing. I think we got away with that. So, yeah, it's to do with energy, so we'll call it dark energy. That's good. It's a good start, and we need to be able to get energy out of nowhere. Do anybody have any ideas? You could rub your hands together. You would need an awful lot of people rubbing their hands together throughout the universe to generate the required amount of energy, and then they would all need to be eating food, and the food would have energy in it already. So unfortunately, that doesn't actually create the energy out of nowhere. So the solution that physicists came up with to this is to look, again, to something relatively familiar, something that we all know about a bit. Quantum mechanics. Let's do quantum mechanics. That does weird things. In the quantum mechanical world, it turns out that a vacuum, like there is pretty much in the deepest parts of space, isn't totally empty, whatever that means. There's a sort of trace of energy left over, even in a vacuum, and we call it the vacuum energy. Say what you see. And so physicists went, well, it's probably that, isn't it? Let's, I think we're done. That'll be. So are you all convinced by dark energy? There's about 2 people who are, everybody else isn't. I think I'm with everybody else. The thing is, what's going on here, what happened with dark matter and what's going on with dark energy is we're seeing something strange happening in the universe. And then we're reaching for whatever we can to try and explain it. So in the case of dark matter, we reached for what we know about particles, and we kind of applied that as best as we could, and we came up with some ideas, and now we're applying them, and they seem to be sort of working. In the case of dark energy, we did something pretty similar. It's just that the thing that we reached for happened to be quantum mechanics, so it's even weirder. But I suppose the reason that I chose the title for tonight is because I think it's a fair criticism that people make, certainly of dark energy, that the reality of what's going on here could be vastly weirder. It could be much, much weirder. Why do we think that nature is really just doing stuff that we're basically quite familiar with? Or even though this quantum mechanics stuff is weird, it's all been measured in the laboratory. And so we're just taking something that we've done before and scaling it up to the size of the universe. And you could say the same about dark matter. We know quite a lot about particles because we can deal with them here on Earth. And so we take that idea and we just scale it up to the size of the universe. And it seems like a pretty damn stupid thing to do. So it might seem naive, almost. But on the other hand, what happens is that we then take those ideas, we run with them. Well, I suppose, you know, we take ideas that might just be totally wrong, and then we do calculations that might be totally unreliable, and then we come up with numbers that might mean nothing. It's a bit like Tesco's accountancy, I suppose. But then we go and compare with the real universe, and we do find that despite all of these problems, if we're interested in sort of averages, then quite often we are able to get those things right. But I suppose my point is that you can turn that around. You can say, all right, we understand why some of these things come out about right on average. Where things go wrong is when we're interested in something very, very specific. Like, if you're interested in, is the solar system stable? We just don't have an answer. We can tell you, on average, would solar systems typically be stable? And you're probably not so interested in the answer to that question. It's the same as the weather forecast, right? They can say, oh, well, you know, is your house likely to flood tomorrow? Well, on average, this many houses will flood. But you're not really, to be fair, that interested in that question. You're more interested in whether your house is going to flood tomorrow. So the questions that we ask are ones that are deliberately made quite broad. And so it could be that the reality of what's going on is something much weirder, and that we're getting the right answers just because we're asking questions that are broad enough that you know, things work out anyway. But I suppose I have an optimistic view of that. That sounds quite pessimistic. I have an optimistic view of that. It means that when we do finally find out what's really going on in the universe, and it probably is much weirder than we realise at the moment, then all of the work that we're doing at the moment, which might be based on very wrong ideas, might still come out and be very, very useful indeed, because it's all about patterns. It's not really about specifics. And that's all I wanted to say. Thank you very much for listening. I think we have time for questions now.
Tell me what the difference is, if there is any difference, between dark matter particles and neutrinos.
Fermilab. I'm Josh Freeman. No, I'm not at all Josh Freeman. I'm actually the guy standing between you and Josh Freeman just for a couple of minutes. My name is Andre Salles. I work with the Arts and Lecture Series Committee here at Fermilab. We're the group that picks the art series and lecture series performers and speakers, and it's a privilege to do so. Just wanted to tell you a few things that we have coming up if you're interested in coming back, as I hope you are. So on Sunday, this weekend, if you want to make a weekend of it, we have the final concert in our Gallery Chamber series for this year. The Gallery Chamber series is a bunch of intimate concerts. They take place in the art gallery upstairs. And Sunday's concert features Jennifer Gunn and Tim Monroe, a pair of flutists. They'll be playing separately and together. Should be a very good show. That's at 2:30 p.m. on Sunday. On Friday, April 8th, Dr. Phil Mote, I think it's Mote, I'm going to go with Mote. Dr. Phil Mote of Oregon State University will be here to talk about climate change. His talk is called 5 Things I Wish Were True About Climate Change. So that's on April 8th at 8 p.m. On Saturday, April 23rd, we have the Stars of Dance Chicago coming to perform on our stage. That's a number of different local dance troupes that perform a variety of different types of dance. It's always a good show. That is also at 8 p.m. on Saturday, April 23rd. And I've been asked to mention we have a brand new lecture that's just been added to our calendar. That's on Wednesday, June 15th, special day. It's Barry Barish of Caltech, who will be here to talk about the recent discovery of gravitational waves by an experiment called LIGO. Hear that? Yeah, that's exciting. So his talk is entitled Einstein, Black Holes, and the Cosmic Chirp, which is a great title. So those tickets are actually on sale on our website now. The Arts and Lecture Series website is fnal.gov/culture. A couple other things I wanted to mention. If you have not been upstairs to our art gallery today to see the exhibits called Art of Darkness, that is all images from the Dark Energy Survey and of the observatory where that takes place, you really should. After the lecture, you are welcome to come upstairs and look at it. And the art gallery is open Monday through Friday, 8 a.m. to 4:30 p.m. if you want to come back. As some of you may know, we, in addition to all of the lectures and art series events that we put on here, sometimes we moonlight as a particle physics laboratory. We do some science. It's pretty cool. We're always willing to answer questions about that. We have a new brochure that would love to see you all take home. It's full of pictures and information. And we have a free public tour every Wednesday at 10:30 a.m. So on to tonight. I should mention tonight's lecture is completely sold out. We have a totally full flight, so thank you. Thank you all for being here. Very much appreciate it. The speaker tonight, he's a professor of astronomy and astrophysics at the University of Chicago. He's a senior scientist of the Theoretical Astrophysics Group here at Fermilab. He got his PhD in physics from the University of Chicago. He's been at Fermilab since 1988. He was the head of the Theoretical Astrophysics Group from 1994 to 1999. He led the Sloan Digital Sky Survey Supernova Survey, which discovered more than 500 supernovae for cosmic study. And he is a founder and current director of the Dark Energy Survey. Ladies and gentlemen, Dr. Josh Freeman.
Thank you, Andre. Can you hear me? Good. So I want to add my welcome to Fermilab, and where we'll be spending the next few hours talking about the dark universe. It's a big universe, lots to talk about. So to set the context, though, I want to start by reminding you of a few basic facts about the universe that I think everyone should know. So the first fact is that the universe is very old. Anyone know how old the universe is? 13.7 billion. Good. All right, this is a good audience. Yes. You've been reading ahead, or it's older than Bernie Sanders, either way. That's it for the political jokes for the night. So it's actually 13.8 billion years. It's gotten older. So how do we know it's old? Well, there are a number of things. It contains old things in it besides Bernie Sanders. The Earth, we know, is about 4.5 billion years old. The Sun, about 5 billion years. The oldest stars in our galaxy, about 13 billion years. And most recently, observations of the cosmic microwave background that we'll talk a little bit about later have pinned it down to this 13.8 billion years. So this is just an example of some of the oldest stars in our galaxy. This is a globular star cluster, Omega Centaurus, an image taken by the dark energy camera that I'll be talking about later, of stars that are about 13 billion years old. Second basic fact about the universe, it's very big. I'm not going to ask how big it is, because it's really big. So the most distant objects we can see are about this many miles away. That's a lot of zeros. I think this is 100 zeta miles if you look it up. And of course, when we get to such large distances, miles are not a very good unit of distance because it's just too many zeros to keep track of. So instead, we use the fact that light travels very quickly, 186,000 miles a second. So in 1 year, light travels 6 trillion miles. So that defines a unit of distance, a light year. And so this many miles, that many zeros up there, corresponds to about 30 billion light years. So that's the most distant things we see are about 30 billion light years away. And just to set the scale, the sun, our nearest star, is about 8 light minutes away. The nearest other stars near the sun are a few light years away. So the universe is very big. Third basic fact is the universe contains billions of galaxies in it. So if you travel to the southern hemisphere, you have the advantage, if any of you have ever been down to the southern hemisphere, you go out on a dark night when it's clear, you can see galaxies with the naked eye. So just a little quiz. So this is a galaxy that we can actually see from the northern hemisphere too. Anybody know what this galaxy is? Milky Way. Very good. All right, this is a very advanced audience. Great. Does anybody know what that galaxy is? Oh, wow. Right. Small Magellanic Cloud, that's right. And this is the Large Magellanic Cloud. These are two dwarf galaxy satellites of the Milky Way. You can only see them from the southern hemisphere, not from the north. So if you ever do go down south, I urge you to go out in a dark night and see if you can see them. They're quite spectacular. So these are examples of nearby galaxies, and the universe is filled with billions of these galaxies. This is a more typical galaxy, and they're typically about 60,000 light years across, contain tens of billions of stars, and they rotate like this galaxy, like our own Milky Way, rotates around its center with on an average, it takes about 200 million years to complete one rotation. This is also an image taken with our camera. So if we could bring the maybe lights down just a little bit, I want to show you a few examples of some pretty galaxies that we've taken pictures of with the dark energy camera. This is NGC 253. I'm sure you all knew that, in the constellation Sculptor. And this is, of course, the familiar NGC 1566. Also, these galaxies are a few tens of millions of light years away. So galaxies, with their billions of them, they're all around the universe, but they don't exist in isolation. They live in and are shaped by a variety of environments, and in proximity to other galaxies with which they occasionally interact. So sort of like my teenage daughters occasionally interact with me, galaxies occasionally interact with others. Sometimes you find them in pairs or in groups or in clusters of tens to hundreds of thousands of galaxies. And those in themselves form part of a larger cosmic web of structure. We used to call these superclusters. So this is just one example here I pulled out. NGC 1672 is a nice large spiral galaxy in the foreground. But if you look down below here, you see a number of more distant, therefore they look smaller galaxies, in a group of galaxies. And this is sort of the first hint that these galaxies are not just randomly distributed throughout space. They cluster together. Here's NGC 1703 in the foreground, but if we look a little closer, and if you look on the right of that galaxy, again, you see a lot of these smaller yellowish galaxies. That's a more distant cluster of galaxies that happens to be behind this foreground cluster. So galaxies clump together into pairs, groups, and clusters of galaxies. This is a cluster of galaxies. Another image taken from the Dark Energy Survey. Again, all those yellowish galaxies are all in a relatively small volume of space, that being a few million light years across. and they cluster together. This is a very famous cluster of galaxies. This isn't an image from our survey. The Coma cluster of galaxies. Again, clusters are sort of the largest gravitationally bound systems we know of in the universe. Again, a few million light years across, and they contain about 1 quadrillion times the mass of the Sun. So 1,000 trillion times the mass of our Sun, typically. And again, that's composed of tens to thousands of galaxies. Now, Coma is an extremely important cluster of galaxies historically, because it was studied by this character, Fritz Zwicky, was an astronomer at Caltech in the first part of the 20th century. As you can probably tell from the image, Zwicky was quite a sort of irascible character. He was quite an eccentric personality, but he was also a pioneer of much of modern astronomy. He's one of the first to carry out a really major surveys of galaxies. He also is the discoverer of dark matter, as we'll talk about in a minute. Postulated neutron stars, did the first real quantitative studies of supernovae. And in the 1930s, Zwicky studied the motions of galaxies within that Coma cluster. He measured how fast the galaxies were moving with respect to us within the Coma cluster. And he found that those galaxies were moving remarkably fast, of order 1,000 kilometers per second relative to each other. And that was just simply too fast for them to remain confined by the gravitational fields of the other galaxies in that cluster. So this was a puzzle. Why is the Coma cluster still there? Why haven't those galaxies all just streamed away from each other if they're moving so fast relative to each other? And so what Zwicky postulated was that the Coma cluster, in addition to the luminous galaxies we could see, that Coma was filled with dark matter. And that the gravity of that dark matter, the material that we can't see, must be the thing that's keeping the galaxies within the Coma cluster from flying off into extra cluster space. So he really was the first one to study this concept in detail, and concluded that clusters of galaxies are mostly made of dark matter. So an image like this, where we think we're looking at the cluster, we're really looking just at these galaxies that are kind of like sprinkles on this vast ice cream cone of dark matter. And we know the dark matter is there because it exerts this gravitational pull on the galaxies that we can see. All right, now we skip forward, and using Einstein's theory of relativity, so I'll remind you that Einstein reinvented our notion of how gravity works through the concept that gravity is not just a force between two massive bodies. Instead, massive bodies or any kind of energy curves space-time in its vicinity, and other bodies move in that curved space-time, and that's how gravity gets communicated. And using that concept then led Einstein to predict, and then the first real verification of his theory, was that light rays should get bent in gravitational fields due to this curvature of space-time. And so what this means is if I look at a distant galaxy behind a foreground concentration of mass, say a cluster of galaxies, then the shape of that distant galaxy will get distorted because the light rays coming to us get bent by the gravitational field of that cluster. So something that's intrinsically elliptical, looking at the lower right-hand portion, that's behind the cluster and near the line of sight to it, will get distorted into something that appears more like a banana or an arc. And this has now been observed many times in observations from the Hubble Space Telescope and from ground-based observatories. So what you're seeing here is an image from the Hubble Space Telescope of a cluster of galaxies. Those are the big, bright galaxies. But then you also see these faint, wispy, very elongated structures, these arcs. And those are images of distant galaxies behind the cluster. And the light has been bent passing through the cluster, and that leads to these very elongated apparent shapes. And you can use those images actually reconstruct what the mass distribution of that cluster of galaxies is. And so these sharp peaks are where the galaxies in the cluster are. But then in addition to those sharp peaks, you see this overall sort of mountain of matter And that's all dark matter. That's the smoothly distributed dark matter in which these galaxies in that cluster are embedded. And so this is sort of direct confirmation of what Zwicky had found back in the 1930s. So skip forward now to the 1970s, and astronomers were studying the motions not only of galaxies within clusters, but of stars within individual galaxies. So this is the galaxy M33. It's a spiral galaxy similar to our Milky Way. It's rotating around its center, and you can measure the rotation speed of those stars around the center of the galaxy. This was done by Vera Rubin and collaborators in the 1970s. And what's shown here is a plot of the rotation speed in kilometers per second as a function of distance from the center of that galaxy M33. Now, what we expected is that as we move out from the center of the galaxy, the stars should be orbiting more and more slowly, because once you get far enough out, there's no more mass. It's just you've enclosed all the stars. And so you would expect the rotation versus distance to look something like that lower dashed line. And that's very much what the rotation curve of our solar system looks like, of planets moving around the sun. The farther the planets are away from the sun, the slower they're orbiting, because gravity is weaker. Instead, what Rubin and her collaborators found was that the rotation speed of stars around a galaxy keeps increasing and then sort of flattens out at a much higher value than would be expected just from the gravity of the stars contained within that galaxy. And this was again evidence that the bulk of the matter of the mass in this galaxy was not contained in the stars that we see, but was in fact contained in some broader distribution of dark matter. And so, like Zwicky, Rubin found that the stars in a galaxy